Hi, everyone. Thank you for joining us today. My name is Abira, and I am one of your Solid State Circuits Society staff members. The topic of today's webinar is Hardware Security and Safety of IC Chips, presented by Professor Makoto Nagata Sensei. Today's webinar will be a little over an hour. We will hold a Q&A session in the middle of the webinar and also after the webinar. Attendees of the webinar have an opportunity to earn a certificate of participation, and I'll post a link and details on how to obtain the certificate in the chat section of the dashboard. The webinar slides and video will be posted both on the SSCS Resource Center and YouTube within a week free of charge. If you have any questions, use the Q&A section of your dashboard to ask questions. I would now like to invite Alvin Loke to introduce our speaker and give a few welcoming remarks.
Thank you, Abira. Hey, good morning, good afternoon, good evening, everyone, where you may be joining. Hope you and your family are staying safe through this pandemic. We're absolutely thrilled to have Nagata Sensei to give this talk. So let me say a few words to introduce my good tomodachi or friend. Makoto Nagata received his PhD in electronics engineering from Hiroshima University in Japan in 2001. He joined Kobe University in 2002 and is now a full professor in the Graduate School of Science, Technology, and Innovation. He is very prolific in our Solid State Circuit Society, where he chairs the Technology Direction Subcommittee for ISSCC. He also serves as a SSCS AdCom member, leadership, as well as currently a distinguished lecturer. He is also an associate editor for the IEEE Transactions on VLSI Systems. So he has spent many, many years as a symposium on VLSI Circuits committee member. He has been risen through the ranks, having been the technical program chair, symposium chair, and an executive committee member. And lastly, he has been, and certainly not least, he has been extremely active, having chaired the Solid State Circuits Society Kansai chapter. So without any further ado, thanks again Nagata Sensei for this incredible talk you're about to deliver to us. Please take it away. Thank you. The floor is yours.
Thank you very much. Thank you, Alvin, for kind introduction. And good afternoon, good evening, and good morning, everyone. I'm Makoto Nagata from Kobe University, Japan, and I will try to explain what we are doing on the hardware security and the safety in terms of the integrated circuit designs and related technologies. Okay, this is the outline. I will be briefly talking about some research backgrounds, and I will define the EMC problems and from the IC chip design point of view, and I will provide some mitigation techniques. And then I will switch the topic slightly to the different world, hardware security, but it's quite relevant to the one I will talk about on the EMC. So 2 and 3 are well tied up. I'd like to try. And then I will have some short break for the quick questions. And then I will go to the IC chip techniques against leakage problems and brief some conclusion in the last moment of this presentation. So this is the background. So we have many systems, as you know, and the IC chips, VLSI systems, are always in the heart of those systems. And of course, we are very much concentrated on designing the circuits for the particular specifications and functionality as well. But if we look into the world, we see many diversified underlying problems, very proximate to the IC integrated circuit design field. One is the safety and the reliability problems. Of course, we have many physical and many different type of principles to maintain safety and reliability, but I will focus on one of the aspects called electromagnetic compatibility, EMC. this is quite related with the design of the circuits. And also sometimes we are using the specific packaging technologies. And also if we look on the other side, we need to consider how the data are secured and how the information could be managed in well-privacy way. So in those aspects, we need to have the good sense of the hardware security in the design of the IC chips again. So all the electronic systems needs to concurrently fulfill security and safety requirements, and which are always backed deeply by many different technology disciplines that we all need to know the ideas. Okay, this is one chart, especially in the one of the application systems that we may pick up the automotive, the vehicles. Nowadays, everything gets autonomously working. For instance, the car can drive without any special driving technique that they can smoothly go and bring the people to the right place. And even more that in near future, we don't have to command, or we don't have to handle the cars. The cars can autonomously let you to lift to this specific place safely and securely. But obviously, for those cars, we need the many IC chips, many the VLSI systems inside the car. But the cars are now connected to not only for the information world, but also for the powering systems. The connected vehicle, sometimes we use this terminology as the case where the cars are connected to the power grids, because all the cars nowadays needs the energy coming from the electricity. So in that sense, the cars needs to be compliant with the electronic systems compliance or regulations like electromagnetic compatibility regulations. If we see the regulation called ECE R10 set up by the WP29, which is the World Forum for the vehicles in the regulations viewpoints. Every car needs to compliant with those ideas if the car manufacturers wants to sell the cars, especially in Europe, for instance. But I think I would say that those regulations are nowadays compliant by the vehicle manufacturers in the whole world. And under these documents, EMC is defined. EMC stands for the electromagnetic compatibility and includes two aspects. One is EMI. This is the electromagnetic interference, and also EMS, electromagnetic susceptibility. Susceptibility is the area of the immunity, which means that how that electronic systems can be resilient to the incoming noise or radiated or conducted disturbances coming from the outside. This is the EMS. And also all the electronic systems needs to comply with the level of the noise emitted from their operations, control of the unwanted radiated and conductive emissions during the operation of the system. So if we have electronic vehicle like the one in the photo, those will be placed in the anechoic chamber, and the antenna will try to capture what the EM electromagnetic waves coming from the car, or the antenna may radiate the big power EM waves into the injection into the car. How that car can be tolerated. Those are real sketch of the experimental scene. And yes, we need to make measurements and try to make sure that all the cars as a whole and also the electronic subsystems in the car are compliant to those regulations. This is the actual standards in the world. So we need to consider that the results in the design of the IC chips. So this is one of the sketch of the emission side. This is a case when that we have the wireless power transfer systems for electronic vehicle. This is sometimes we call it as WPT. And here is a controller of the WPT, and we have a horn antenna very proximate to the surface side of the controller. And then the picked up the noise are given in the chart on the right, sorry. The horizontal axis gives you the frequency from 5 megahertz to the 6 up to the 6 gigahertz, and the vertical axis gives you the measurement results, the strength of the near field in each of the frequency component. The black line stands for the case where WPT is completely turned off. This is a kind of the background noise. But once we turned on the WPT system, the noises come up, and the red lines give you the big jump of the nearby field if we have the antenna just in front. And those three zones are specified for this particular slide because in each of the area, there are some wireless standards are operating. So the noise may interfere with the operation of the radios. Undesired radio waves in the frequency band of interest in the wireless communication system like 4G and 5G. We need to consider the interference. This is a image of the EMI, the experiments. If we consider the EMS, the susceptibility side, this is another typical setup of the measurement technique. In this case, I pick up the gigabit Ethernet as a system to be tested. The BCI stands for the bulk charge injection. In this case, the signal generator creates the sinusoidal wave, and those will be injected into the coil and coupled to the wire lines from the data quality analyzer to the layer 2 switch of the gigabit Ethernet. It's standardized, the one well-known one, 1000 base T. And of course, without noise, the quality analyzer can communicate with the layers to switch without any errors. But once we inject the big power, something might happen. The measurement results are shown on the right. The horizontal axis gives you the frequency of the injections, and the vertical axis gives you the power, net power. Some of the power will be reflected back to the amplifier because of the impedance mismatch. Those will be measured by the directional coupler with the power meters. And the forward power and reflected power will be measured. And then we can calculate the net power. Means that the power injected into the Ethernet cables. And green dots means we see that nothing happened. We can have the full data rate, even with the incoming disturbance. All the green dots are good. But we see some red points. In this area, we don't have any data communication because of the incoming disturbances. Narrow zone, I would say this is the frequency of something like 80 megahertz, or in that frequency range area. The sensitivity comes from the fact that in this case, the 1000 base T, the signals running on the Ethernet category 5E cables have the bandwidth less than 100 megahertz, and all the signals are meaningfully communicating in this frequency region. So this is a reason why that the incoming power will be interfering with the data communication over this Ethernet cable. So we need to have some technique to eliminate those interference coming from the outside of the cable. The relation with the automotive world is that we will use the Ethernet regularly in the car over a single copper pair. Normally, the typical bit Ethernet uses 4 pairs in the big cable, but in the car segment, only a single copper pair will be used without shielding. So this means that those measurements will give you idea how that the systems can be tolerated in the incoming disturbances. So this is the idea of the EMS type of the I need to have there's a pointer of the experiments. Okay, so we have the test specifications widely internationally defined for the measurements of the emission and also the measurements on the immunity. The IEC 61967-6 stands for the magnetic probe method. I will give you some actual ideas in the next some slides. But anyway, here the measurement method is defined for the frequency range from 150 kilohertz to the 1 gigahertz. And conversely, that the measurement method on the immunity is defined as a direct RF power injection in this case, and in the same frequency regions. Those are defined in the 22 or 3, or I would say that's 20 years or more in the past. And the frequency of interest was below 1 gigahertz, but nowadays, of course, that we are looking into the measurements over the 6 gigahertz because we have many wireless systems in the frequency regions from 1 gigahertz to the 6 gigahertz. So if we see chip that the size of the die could be in the magnitude, the size of the 5 millimeter times 5 millimeter, and all the circuits are within the die, and the noise or EM radiations are coming from the operation of the circuit. That means the source of the noise are always confined in the area of 5 millimeter or below. But the EM is always emanated or radiated. You can observe the EM waves on the board in the range of 10 centimeter or so. And even further, the EM radiation can be captured by the antenna placed 1 meter away from the die. So the EM problems, we need to consider all the systems, not just the chip, but also considering the package, board, and even the chassis, and for the propagation to the sensitive part of the system, even in the room. So the EMC problems need to be solved, not just as IC chip, but also from the distant the positions. So we need to see all the areas away from the chip. The MP, magnetic field probe, is often used for the IC chip on the emission of the noise from the circuit. So this is a sketch of the actual measurement. Here is the magnetic probe. The probe tips are very closely placed on top of the silicon chip. at this point. The sketch is shown here. The chip often packaged in a flip chip way. That means the circuit side, CMOS side, are faced down and to the interposer. Probably that's a plastic interposer. And the backside of the silicon is open to the magnetic field probe. So position 1 is located the backside area. And the similar measurements can be doable on the power supply line on the printed circuit board. Of course, the currents are flowing to the system power supply with the circuits on the silicon. This is a power line. So the measurements can be can give you the idea of what's the strength of the emission when the circuit is operating on the area of the chip or area on the printed circuit board. The measurement results are shown on the right. Horizontal axis giving you the frequency components. In this case, the circuits, digital circuits, typical digital circuits, were operating at the clocking frequency of 106 megahertz. But our measurements are spread from 10 megahertz to the 5 gigahertz. Once we measure the radiated noise, we have the clear components. I would say it's the harmonics of the 106 megahertz clock frequencies. And if we look into the 20th harmonics at the 21 gigahertz, we have the minus 30 dB, almost like a minus 30 dBm. And if we measure on the power supply line on the printed circuit board, but if we move the measurement point to the backside of silicon, we don't see big difference. Still, we see the minus 35 or something like that. Not so big difference from the measurements on the power supply line and on the backside of silicon. So everywhere we will measure the significant magnitude of the high order harmonics. Once again, the circuits were operated at 106 megahertz, not so high frequency, but the noises are always distributed over the 5 gigahertz range. And once we measure that, we can make some calculations. So here are the order of the harmonics. 9th order 954 megahertz, 18th order 1.9 gigahertz, and the 20th order 2.120 gigahertz, as I mentioned. The noise power density captured by the spectrum analyzer was minus 150 dBm per hertz. This coincides with the LTE band 1, exactly in the same frequency. The downlink frequency, some frequency, the regions, but the 2.12 gigahertz is located in the middle of the band 1. And this was the measurement results. And if we assume that 1 megahertz, the equivalent bandwidth used for the LTE receiving side, the channel power was calculated like minus 90 dBm in the frequency of the band 1 at 2 gigahertz. This can be calculated. This is a number of the power, but we need to have we need to characterize the undesired radio waves as the field, E field or magnetic field. In this case, electric field is calculated as 350 microvolt per meter if we use the dipole antenna nearby the chip. This size is quite significant because typically in the city area, you have the cellular user equipment in your hand, and the E field is like 100 microvolt per meter. This is a kind of the order. Of course, that the numbers should be varied in the location of your handset, nearby the base station, or very far from, or in the country area, or in the city area. Everything should be different. But still, I would say that those numbers are quite well, comparable. That means if you have the big chip without any concerns on the EMC in the design, the UE, your LTE receiver, can be affected. This is a kind of the interference issues. We can calculate what's the impact on the wireless channel by using the electronic system level simulation. Here is the simulation model. The 4G, 5G class chip can be captured in the ESL simulation framework with RF models. The LTE modulation or 5E modulation can be given by the system level simulator. At the same time, we can inject the noise. Those noise can be captured as in the last slide. Those data can be given to the simulator and added to the input. And the output can be demodulated in the LTE framework. Of course, those can also be done by the simulation. So the measurement results and the simulators can combine, and then give you the idea, oh, that measured noise can reduce or deteriorate the performance of the RF receiver. Without any noise, this receiver has a minus 100 dBm in the 5 MHz channel bandwidth for the minimum receivable signal. But once we have noise, the minimum receivable level will increase up to minus 92 dB or minus 87 dB. That means almost 10 to the 15, 10 or 15 dBm deterioration we could see because of the noise. So noise measurements can be quite easy. Just we can use the magnetic probe, as I showed you in the slides earlier. But the measurement results needs to be calculated or needs to be used for the simulation on the impact on the RF receiving the characteristics. Of course, we have some techniques to solve. There are the flip chip packaging. In that case, we have some areas between the silicon surface to this interpolar. We can insert some magnetic composite sheets to absorb the EM power. Of course, we can put the good capacitor nearby the circuits. If we can use the fan-out laminates, that will give you the very close location of the land side capacitors to the circuits of the noise source as a noise source. And also we have the 3D chip stacking techniques. In that case, that we have distributed capacitors in the whole stack, 3D chip stack. That will also reduce the noise. Once we reduce the noise, the measurements will give you the idea of how many dBm, how many dB you can have the attenuation of the noise. And then once again, we can use the system level simulator to see how that the system performance can be improved. In this particular case, if we have the magnetic absorption film for the EM noise, and the reduction of the noise happened. And then the noise suppression gives you the chance or opportunities for the RF receiver to have the better, the minimum powers of the strength, minimum strength of the power to be received. Okay, so the next is the how those ideas can be connected with the hardware security field. Once again, but we can use the magnetic field for the measurements, a magnetic probe for the measurements. Once we measure the wave shapes, then the attacker or adversary can analyze, make some analysis on to extract some secret information just from the measurement results. Simple for analysis, in this case, that the measured waveform will be straightforwardly analyzed as a signature. Differential power analysis, correlation power analysis, we can use the set of waveforms to make some correlation with internal data set, the processed by the digital circuits in a chip. And the local EM analysis is it's a kind of a combination, but in this case we use the very tiny the EM probe to capture the waves coming from the chip just on the top or many other places. I will show you the exact results. And the image of the measurement setup is shown here. Here are chipped and assembled on the printed circuit board, and the magnetic field probe are scanned over the printed circuit board and capture the wave shapes just by using the oscilloscope. Okay, there are some different style of the cryptographic engines in the design. The one category is private key crypto. The other one is so-called public key crypto. In the private key crypto, a single private key is symmetrically used for both encryption and decryption. And in this case, the waveforms, EM waveforms or power waveform are relevant to the set of the data manipulated in the crypto processes. Differential power analysis or correlation power analysis are the often used for the attacks. In the case of public key crypto, the keys are different. One key for the encryption and the other key for the decryption. And those are quite tied up in the mathematically in the crypto algorithms. In this case, power side channel leakage analysis, simple power analysis can be applied. Of course, there are many diversified ways of protecting the crypto circuits not to emit the EM waves with the internal data, but there are many battles between the attacker and designers. And what we can do? Okay, so the magnetic field probe can again measure the chip, measure the location of the chip and also location of the printed circuit board on the power lines. At the same time, we can also use the oscilloscope probe just to put the chips onto the power supply lines. Here are local resistivity or impedance. Because of those impedance, we see the voltage variations. Unfortunately, if the current flows, the voltage happens that can be captured by the oscilloscope. And here is a field map. The magnetic field probe can scanning over the printed circuit board, as I mentioned. This is the measurement result when the chip in the BGA is located here, and there are power supply lines on the printed circuit board. The brighter area, brighter color means that the higher level of the field, the strengths. And the blue ones are very stable, very the silent area. But we see most of the areas surrounding the dies are in a bright area. That means we can measure the noise everywhere, not just on the die, but also on the power supply lines as well. And once again, that the noise can captured by using simply the oscilloscope with voltage plots on the power supply line, or we can use a magnetic probe by capturing the magnetic or electric coupling to the probe. Those are the some analysis given to the measurement results in this case. The chart on the left gives you this is well, try to explain. This is a chart made for the explanation, because this is a simulated power current of the private key crypto like AES, in this case AES. With a different set of the input vectors or a different set of the plain text given to the AES core to encrypt. We obviously see the difference in the size of the power current at a particular clock cycle. Those difference will give you the idea of the correlation with the internal logic switching, or sometimes we can use the Hamming distance in the register, data register, how many bits flip in this specific clock cycle. The larger number of the flips, the larger size of the drops we can measure. Those are the source of the correlation and the source of the leakage of the secret key information. In this case, we call it, this is the measurements of the power signatures. And for the public key crypto, we can use the EM signature by using the magnetic probe, for instance. In this case, we intentionally put the key as a quite simplest case, like O0 or O1. If we use the elliptic curve algorithms, for instance, the key number 0, key bit 0 means a specific calculation. It's like a point addition, or those kind of arithmetic operation will dominate in this area. But if we put the bit all 1, in this case, different calculation like point doubling will happen. It's not accurate explanation, but it's a kind of the image. So the O0, you will have all the same calculation happening in the crypto operations. All 1, the other, but the same calculation will be continuing. But obviously, we see the 2 different signatures in the EM waves. And those can be naturally captured in the frequency zone, frequency domain. Horizontal axis gives you the frequency, and the vertical axis gives you the magnitude of those particular signatures. In this case, 1 lower frequency at the 22 kilohertz, some the patterns shown. And also on the 39 kilohertz, we see another peak. This is coming from the bit pattern of the 0. So here, the one metric is how we can reduce the difference. This is a kind of the delimiter, the frequency, because 1 has a particular time length and 0 has a particular the other time length. That means those happens. We often see the 2 different delimiters, 1 for the 0, the other one for the 1. So we can change the design, or you can change the frequency of the clock frequencies, but always we would see those delimiter powers in the frequency components. So that can give you the idea how we can reduce those delimiters to reduce the leakage. So there are some other the assessment numbers, like the one for the correlation-based side channel leakage. In this case, the number of the measurement traces needed to disclose all the key bytes. Those are the one very obvious or straightforward the metric. So that means how many wave shapes we need to capture those leakage in the measurements. Sometimes just 10,000 wave shapes, but sometimes in some good designs that the number will be increased to the 1 mega or 1 billion. So the larger number, better design. This is a MTD. The other one is the one thing more deeper. We don't have the clear model of the correlation, like the Hamming distance model or something. But even in the case that we may use the statistical analysis in the case where 2 different the measurement groups can be defined. One is a case in the simplest case. One is a case with a fixed input. But in the actual the chip or actual device, always we have some fluctuations like a voltage or like a temperature or like the timing jitters as well. Those will give you some the statistical spread of the measurement results, even with the same input vector. At the same time, we have another set of the measurement with a randomized input. So if we see the difference between the probability of the, for instance, wave shapes or the frequency components, if we have the clear difference between the case with the same input and the case with a random input, in that case, we may have some statistical significance in the two groups. And then we may say that there are some correlations between the measurement results with the data set. In this case, we don't have the clear model, but we would say that there might be potentiality of the leakage because of the data set gives you the idea of the two different sets. One is a fixed, the other one is a randomized. We see the statistical significance. In this case, that the t-test value of 4.5 can give you the idea of potential leakage. The other ones, as I mentioned, the p delimiter can be the case for the signature-based leakage. And also, similarly, we can use the length of the calculation or the length between the peaks, and those can be used to characterize the power waves as another metric of the assessment. So this is the last slide of the first half. Obviously, we see the similarity in the discussion among the EMI and the EMC viewpoint and hardware security viewpoint. So EMI analysis normally uses the level of the noise, but the SCCA analysis needs that not just the level, but the correlation with the internal operation of the circuit. So we need one more step inside of the operation of the circuit to be recognized. And the EMS, I didn't mention much about this because of the time limitation, but there are the immunities that mean how that the system can be tolerated against the incoming power. But at the same time, those can be translated as a photo injection, that the immunity gives you some erroneous operation, and after the erroneous operations, the cryptographic engine gives you the wrong results. How that wrong result comes up, those analyses give you the internal, the operation of the circuit, and finally disclose the key. So those two things are quite relevant, and the designers can use the knowledge for the good safety in terms of the EMC and the good security in terms of the cryptographic engine designs. Okay, so now it's a short break time for the quick questions, if you have.
Yeah, Nagata Sensei, thanks very much. Yeah. So I had a question I want to ask related to, you talked about different ways to reduce the interference, for instance, using a magnetic layer underneath and a couple other techniques. Is there research done, for instance, looking at the actual encasement of the cell phone to reduce? Right? Obviously, you can't completely attenuate what you're transmitting and receiving, but like using an actual enclosure somehow around the cell phone to reduce the interference.
Okay, very nice. Thank you very much for the question. So yeah, we have many proposals. We have made many proposals how that we can reduce interference in the real chip, but the adoption is not easy. So the important point is that how we can produce the noise suppressor in the band of interest, because you cannot insert the noise suppressor in front of your receiving chain, because that may reduce also the incoming important the signal. So the noise and the signals are always conflicted to each other in the same band. So that how we can reduce just the noise, not the signal. This is the idea why we choose the magnetic material that can put only on the digital part or noise generation part, that can locally absorb those noise. That will not affect the incoming power to the receiving chain on the analog side. Those considerations. And also finally, we are trying to set up the design methodologies, how that we can put those noise canceling or noise suppression, the materials or the structures to the exactly or the right place in the whole chain. Those the constellations are needed, and this is a reason why it's not easily be adapted by the actual serial forms.
Got it.
So far.
So this is kind of to a related question that's been asked by someone on slide 12. Obviously talking about the magnetic composite sheet. So I guess the question is, how does it really work? I assume you're trying to essentially reduce the attenuate magnetic energy from spreading, right?
Yeah.
Okay. And also, as the EM emissions from the top metal layers can also be captured, the power supply line connected to the interposer can also be probed.
Mm-hmm.
I'm not sure. Well,
so
anyways,
question is that. So question is how does the magnetic composition can work, or what?
Yeah. I
okay.
think this is a general question of how the magnetic composite sheet. I mean, I'm assuming,
yeah. Basically, the magnetic component sheet is the way of absorbing the noise locally. You need the magnetic field as close as possible to the source of the noise. That means if we can put the magnetic composite sheet in front of the CMOS die, from that consideration, we might include the magnetic composite sheet within the flip chip. Oh, this is a flip chip type of the assembly. So this is a case. We may have the space between the front side of the circuit to the a plastic interposer. In that case, we can insert the magnetic field underneath the or front side of the sequence CMOS.
Sure.
That can make.
You're just trying to absorb the energy away, right?
Yeah.
Okay, another question. Can we expect the tolerance of an IC chip to RF injection, in other words, immunity, also be also to fault injection?
Oh yeah. This is the case that, for instance, all depending on what kind of the RF injections. But in the case, for instance, the injections are coming from the signal line. In that case, you may insert some the suppressor at the ESD point. You always have the pad and ESD, and then going to the circuit. In that case, the ESD can use the way of absorbing the excess power, and then the circuit will be protected.
Okay.
This is the one way.
And last question before we move on, I guess. How do we deal with EMC and hardware security simultaneously co-designed?
Oh, that's a very good and big question. Yeah, I will try to answer in the next part. That I think the one is the simulation techniques we really need. I think that because by design, we need to consider both EMC issue and hardware security issue at the same time. That should be handled by the simulation models.
Got it. Okay, thank you. Yeah, so anyways, if you can please continue with the rest of your presentation, the second half. Thank you.
Okay, thank you very much for your good questions. Okay, I will move to the second part. Okay. Number 4 in the item list, the IC chip techniques against side channel leakage. So normally the cryptographic processors are surrounded by some other circuit constituents or the circuit the blocks modules, like the one that the interface that digitally decouple the outside world to the cryptographic processor. And the PMC stands for the power management control. That will give you another way of the isolating cryptographic processor from the outside in terms of the power delivery. Sometimes we can place the DC-DC converters within the power management control module. Now, of course, we have the PLL phase lock loop for giving the clock frequency given to the cryptographic processor. That can also another wall or the isolator. from the frequency generation point of views. Those will be protecting in some part. But as shown in the first half of my presentation, if you have the magnetic field probe, very tiny one, you can scan the probe over the die. That means, yes, you can make some the isolation logically, but still you have the space for the attacker to look into by using the magnetic probe. That can give you the chance to see just on top of the cryptography processor, for instance. That will not be covered by those surrounding circuits. That can happen not just for the passive attack by using magnetic field probe to measure, but also for the active attack. Sometimes the tiny or the focused laser can come to the cryptographic processor, and that will give you the injections. So we need to have the multiple level of the protections for the chip to be very highly resilient against the attack. To explain that we have some the list of the items that can influence on the attacks. For instance, from the attacker point of view, if you have the different types of physical medias, you can use for the extracting the information. For instance, the passive attacks, you can use the EM or photon radiation, voltage on the power line, of course, the power current flowing on the power lines that can be used for the side channel attack in the passive way. And also, if you have the EM injection, laser injection, ESD guns, and also glitching injections, those can give you the way of the active attacks using the fault injections. Those are physical media. And of course, that the attacker needs to see the point of the attack, but those are quite the affected by the assembly structures. For the ASIC, what's the way of the chip in the assembly? For instance, a wire bonding face up or flip chip with bumps. Those are difference in the attacker point of view. And how the whole chip are molded in the plastic materials or chip on board with fully covered by the plastic mold or even just the open. Those are difference for the attacker's point of view. And even for the FPGA, the chips are nowadays stacked. So how that we can go into the internal layer or tier of the SED chip stack, those can be also the consideration by the attackers. Or if we consider those things from the attacker side of view, that will be conversely for the people to protections. The designers needs to know the way attackers are doing. So one other thing is that if we can understand or if we know what's the actual noise wave shapes happening on the die, the EMC measurements are always done on the outside of the die. But as I mentioned, all the EMC problems are confined within the chip, within the circuit of interest, finally. So in that case, from that understanding, we need to see what's actual wave shapes happening on the die. That will give you the clear image or clear advantage as a designer to make things better. So this is a very simple design case of the on-chip monitor. Just we have the one source follower to see the voltage variations happening on the VDD or on the PSS. This is a kind of the DC offset provision by the circuits, since that we need to measure the highest voltage in the chip or lowest voltage in the chip. This is the reason why we need to have the source forward here. The output of the source forward can immediately be digitized just by having a simple latch comparator to make the comparison with the difference voltage at the strobing time point. The very traditional AD converter, the structures that can be given for the internal noise waves forms like this. In the case of the AES, 128 bits, the very clear shape given in seen on the core VDD and even on the core VSS. As I showed you in the previous chart, parts that the drops will give you the idea of how many bits flipped internally in the AES. Those can be considered as the source of the leakage. In that case, how we can reduce the height, or how we can decouple the noise shape with the internal data. Those needs to be considered in the design phase and checked on as the source of the noise creations. And for the different types of the design, like a public key types, like ECDSA in this case, all the calculation or the processing will be done after very long clock cycle, very large number of clock cycles, after the 600 microseconds, the CDSA processing will happen. So this is the reason why we need to see the P power of the delimiters. Obviously, we see some patterns. Those are captured as the specific power component in the measurements. Once again, this is a power side, and also this is a ground side. So both power and ground give you the same, almost the same level of the leakage in the sense of the power grids, power delivery networks. So once we got such the measurement waveforms, how we can use that knowledge that, okay, that in that case that we think about the modeling. So here, general model of the system level power noise analysis. This is sometimes we call it as the chip package system board model. Here is a chip model, and here's a package model, and here's a PCB models. Those are connected together and supplied by the external source. This is the ideal case in this case. And we need to have the chip model that should capture how the internal data flips or internal logic switching happening. Those need to be captured in the chip model. I will show you in the next slide about the actual model of the chip. And in between the digital circuits of interest and the package models, we need to have the power converter models as well. And those will be combined together and make the simulations. So what's the chip power models stand for? In this case, the actual active part of the digital circuit will be captured in the two different sub-models. One is a power current model, and the other one is a power network model. The power current model captures the dynamic consumption current or demand current during the operation of the cryptographic circuits, for instance, or any kind of digital circuits from the EMC standpoint. And at the same time, we need to have the power network model because the passive part of the network will impact on the level of the noise. So power current active part of the model will be captured in this way. So we first characterize the standard cell library because all the digital circuits are placed, the logic synthesized and automatically placed and route. So in that sense, the standard cell library can be pre-characterized beforehand for the incoming logic states and outgoing logic states, and what's the level of the voltage, supply voltage, and the temperatures. The parameters are mapped in the final list of the power current of each of the standard cells, like inverter, NAND, and flip-flop. Those have the full sketch of the power current models. And then the cell characterization, as I mentioned, it will create the standard cell power library. And the Verilog netwidth will give you idea of the toggle information during the operation of the digital circuits. Those toggle information and the power library can combine to create the power model, active power model. In each of the time period, which the standard cell will be flipped, those will be translated with the power current model of this particular logic cell, for instance. So in the time domain, all the operation of the logic cells will be converted to the power current models. And full-chip power delivery network models will have the on-chip model, passive model, and also the off-chip package and assembly models. Those are fully combined together, and finally, simulations can be done. So in the AES, I think you can imagine that as I mentioned, in the last moment of the AES, in this case, last case of the AES processing, the data register will make some flips internally because of the internal calculation of the AES, advanced encryption standard, the calculations, and how many bits flipped in the data register will give you the idea of what's the level of the noise coming from the data register at that time point. Those two will be make some the leakage in the correlation due to the correlations. So case study of the simulation, this is a chip having the AES and some other cores in the area of the digital part. And that can be captured in the chip power model, as I mentioned. The size of the AES is not so big. It's just like less than 50 kilogauge. So that can be easily handled by those models. But we need to have the very nice fine-grained PDN models. That will give you another capacity for the simulator. But I will not mention in detail, but in this case that we can capture all the PDN, and even the sequence subset can be included in that model. And the simulation can happen with the different test vectors. In this case, 100, 1500, the different plain texts are given for the simulation of the last round of the encryption of the AES. And the simulation results give you again that the data V for the Hamming distance. So in this case, this design is not so good because you have the clear difference in the simulated voltage waveforms among the different plain text. So that will surely give you some leakage. This is a results of the simulation. Horizontal axis gives you the number of traces, and the vertical axis gives you the rank of the guessed key bytes. The rank number 1 means that the key bytes can be surely give you the actual secret key. So in this case, the blue lines, only the 3,000 traces, all the key bytes are determined. And in the measurement-wise, in this case that we have the actual sequence, so that the measurement-wise, the similar trends, but we need some other 5,000, but not so much difference. So, but the simulation can be always pessimistic because this has a clear correlation internally in the part traces. So this gives you the idea that how that we can make some things, make the design changes or make a place and route changes. Those will be iteration needs to be done by the designers, but the simulator needs to give you the results in the prompt way. So this is a very the interesting sketch. Those can be done only by the simulation because the left-hand side This is the so-called power side channel leakage correlation score. This is the area of the chip. And like the area shown on here, this is the area. And in this area, where the source of the leakage happens, the simulation can do the side channel leakage analysis at each of the point in the die. And let give you the highest the correlations. So in this case, that we need to change something in that area to reduce the number of the vectors needed for the disclosure key. So here on the right-hand side, we show you the two different designs. One is the one exactly the same one as shown in the previous chart. The 20 times 100, 2,000 or 3,000 test vectors and just needed to disclose all the key. This is not good case. But if we change the design, the number can be slightly changed. Of course, that the leakage trend can still be obvious, but the number of the traces finally needed for all the key bytes to be disclosed will be increased by 5 times in this case. But this is one example. So you can make some changes and then you can simulate, and you would see the which is the best design. So this is the final part of my presentation today. So I showed you the measurement technique and also simulation technique. But finally, what we need as the designers, the circuit level countermeasures are really needed. Of course, that the countermeasures should be tested by the accurate measurements and tested and simulated with the full chip package system level simulation in the design phase. But what the options we have as the circuit level countermeasures. So one is a side channel leakage mitigation techniques. In that case, power equalization is one of the way. And the power noise filtering and EM frequency dithering can also be other ways, and so forth. Side channel attack detection is another metric or another methodologies. In more or less, we may have some the leakage, unfortunately, because the attacker can use different types of techniques to dig into the heart of the security chips. So that we need to some other method to protect. In that case, we can sense the attacks, passively sensing environmental variation. So how that the change will happen due to the trials by the attackers. Sometimes the magnetic field, sometimes the temperature will be changed or voltage will be changed. Those can be sensed by the chip itself. Or the active sensing of the physical attacks can be doable, because if you radiate laser or if you radiate the EM, those can be sensed by the sensor circuits on the die. Of course, that we can use some logical detections on the errors happening on the data path of the cryptographic engines, for instance. Those can happen. So LTO, this is a well-known technique for the regulating the voltage given to the circuits on the die. In this case, the external voltage of 3.3 volts is given at the Vx, and LTO reduces the voltage and stabilizes the voltage given to the core circuit at the 1.5 volt, for instance. This is a very nice one, and potentially this can make some barrier for the leakage, but that's not true. Because naturally speaking, that LTO is a low pass frequency filters. They will exhibit low pass frequency characteristics because the change in the voltage will be stabilized by the error amplifier by consuming the current from the outside. That means voltage changes will be naturally translated into the change in the currents. So this means the DC components will not be blocked by the LDO. This is the reason why the people are developing the power supply equalizer. This is another idea. So don't try to stabilize the power as with the operation of the circuits. This is always try to make the power stable, even with the operation or without of the core circuits. Regular consumption of the power at the constant way. The one well-known design given by Tokunaga in 2029, this is the kind of every time the charge will be given to the core and consumed by the this short switch. This regular switching gives you the try to hidden what's the actual the charge consumption made by the circuits connected at the BDD core. The other designs nowadays very actively reported in the ISSCC recently try to use the digital LDOs, try to see the voltage difference by the AD converter, and the digital output will be given to the digital controller to make the voltage stable. So this is the change, the difference from the analog LDO to the digital LDO is that in this case that this design can try to eliminate the dependency of the voltage variation on the data used in the cryptographic engines. Very smart idea. And the other way is not use the voltage, but use the current. The current will be stabilized. This is a kind of the disturbed current sources, but digitally controlled. This is another way. So the MTD, the number of the traces needed to disclose the key is starting from the some thousand, but 10 mega, 1 mega, 10 mega, and finally the video. Those are good. But one thing I need to say is that this is good, but all depending on the circuit scale or what algorithm you are using. Those are always used for the AES in typical case. But if the circuit size gets larger for the public key crypto, the design will need to be changed. But this is a nice idea, but all depending on the design of the crypto engine or some other the digital circuits from the viewpoint of the EMC compliant designs. Okay, so last the idea is that how we can use the sensors, the EM analysis, EM measurements, local EM measurements, as I mentioned in the first part, that micro EM probe, the tiny magnetic field probe can search over the crypto chip or the circuits. So this can be kind of the snooping technique considered not invasively. That will not affect the whole operation of the circuit because this is a very passive way, just try to capture the EM naturally coming from the crypto circuits. But in reality, there are coupling between the probes with the circuits. So the EM observation is not the invasive. Always this will give some changes in the field nearby the circuits. So what's the sensors can be established? The answer is shown on the middle. If we have the two different LC oscillators on top of the circuits to protect, if the sensor is coming, the coupling, the strength will be changed between the 1 and the 2. So if the coupling changes, the oscillating frequency will be changed, but the change will be different for the 1-turn coil and 2-turn coil. Just a very simplistic sketch in this case, but anyway, the sensor to probe distance is on the horizontal axis, and the operating or oscillating frequency will be given on the vertical. Those two are different, so that if we see the difference in the frequencies, that we can see something is happening in the field nearby the cryptographic core. So this is the measurement results. If you have the circuits in the chip and the EM probe is coming, the right-hand side gives you the measurement results where probe to chip distance in the order from 0 to the 0.2 millimeters on top of the chip. The vertical axis gives you the change in the frequencies. So the different oscillators give you the different response to the incoming the change in the field. So the change gets larger once the probe is coming closer to the surface. This means the sensor is good in the case when the adversary removes the front side cap or front side materials. Try to make the EM probes closer for the better signal to noise ratio from the attacker viewpoints. So this is the demonstration. Without any probe, those two oscillators are autonomously locked at the same frequency. But if the probe is coming, unfortunately, those two are not in the same frequency. That would be deviate from each other. And that will give you something is happening. And finally, for the safer side, the security, the function will be stopped or terminated or try to go to the other safer operation modes. Okay, so now I would like to summarize my presentation today. So there are, I tried to show you many different pictures in this talk because try to give you the idea of what the EMCs are and what are other securities are in the IC chip fields. But obviously, finally, that I think we noticed that the knowledge is quite complementary among the emission and immunity, and including the device characteristics, the system response, and those are quite useful for the design of the hardware and the software design for the security and the safety. This comes from the fact that those knowledge are coming from the EMC and coming from the hardware security field at the same time, and those ideas can be combined. The IC chip techniques can provide the mitigation and the resiliency for those the EMC and the hardware security problems. So co-design considerations by using the design of the core itself and the touch sensors and power delivery systems, and also the packaging structures with exotic materials. Those can give you the high-level solutions against such a leakage, and also the problems, solutions to the EM problems as well. So thank you very much for your kind attention. And if you have questions, please give me. Thank you.
Nagata Sensei, thank you so very much for a very great talk. A lot of questions are coming in. So one question, I'll just go through in the order that they were asked. So how difficult is it to isolate or probe the crypto logic at advanced technology nodes, lines, say in 7 nanometer or 5 nanometer? Or really does it really make much difference?
Okay, that's a very good question. Yes, that it's not easy to find out where the exact the crypto modules is, but from the EMC standpoint, that always those circuits consume some power. The power are delivered from the outside, so we don't need to place the exact point, especially if you consider the silicon substrate. As I showed you, the ground part of the node shapes, again, they will give you the leakage channels. That means the base material always gives you the the propagation of those information. So unfortunately, you can probe anywhere on the die to extract some data in principle.
Okay. Another question. would detecting a micro EM probe using the two coils work in a practical scenario where another nearby component may have a large EM noise radiation?
That's another good question. So that, yeah, the question is that how that the sensor can work for the different types of the EM the conditions, right?
I think so.
So yeah, that's the kind of the usage models problems. I'd say that if you are in the safer side, that if you see the difference from the stable states to the dynamic changes, your chip can try to hold the secure processing for some time, and then if the environmental changes get stable, then resumes operation. Those the kind of the detection and the operation can be designed in at the system level. This is the one of the answer to those kind of things. But
Okay.
of course, that we have some other sensors at the same time as well.
Got it. Another question.
Yeah.
Is there a difference in measured power values depending on chip points that's used for measurement? I guess
So once again, please.
How locally sensitive is the measurement? Or what is the spatial rate, spatial resolution?
Yeah, I know. But I would say that once again that this is all depending on the design of the power delivery network. If the chip had the power delivery networks that can be unified, all the circuits on the die, I would say there's not so much position dependency because all the currents are flowing in the same power delivery network. But if that design is well fine-grained or the separated to each other by using the local power regulators, in that case, you may need to look around, or you need to have the microprobe with the position accuracy of 1 micron or so. But once again, that still, if you still have the same sequence subset or same materials sharing by all the circuit constitutions, in that sense that you may have another attack methodology that can be insensitive to the positions.
Okay, so basically, I mean, essentially the spatial size of a supply domain is probably much larger than the resolution.
Basically, yes.
Got it. Okay. Another question, PSLS metric, is it based on the TVLA metric or is it calculated differently?
Yeah, well, that's the, okay. This is basically the, okay. This is the EDA technique, so that this tool can handle this tool can capture the wave shape, power current wave shapes at every point, with considering the toggles happening nearby, and the captured wave shapes can be the post-processed. In this case, I would say this is very much similar to the MTD. So how many the wave shapes you need to extract the key bytes? But
okay.
Yeah, this is a very straightforward answer, but the tool gives you the wave shapes. That means you can also apply the TVLA actually in the other the processing step if you have.
Got it. Next question. This is an interesting, a good one. What cipher algorithms are used in recent IoT applications, and what vulnerability needs to be considered? So maybe no one will say what is really being done, perhaps, but I'm sure you have some sense of what's going on.
Oh yeah, one answer is that actually I'm preparing some slide sets for the various symposium on that aspect, and actually in IoT the application space that we are using both of them. It's a kind of the combination of the different types of the cryptos. because public key is good because the public key crypto can conceal the secret keys from the outside, because the outside they don't need the same secret key thanks for the asymmetric key usage. But this circuit is quite huge. Normally they need a large power, so that in that case that for the local or depending on the on the total processing flow, but I would say that after the public key crypto, that the system will switch to the private key crypto for some time, and then going back to the public key cryptos. So those kind of combination will be used in the IoT environment, but all depending on the what the energy source or what what's the I would say that sorry that I forgot the English, but the what kind of the data path, what kind of resources you have on your design.
Got it. Yeah. Anyways, I'll throw in a shameless pitch at this point. So we do have a short course on VLSI in the upcoming VLSI symposium on IoT, and Nagata Sensei, you are obviously one of the invited speakers there. Yeah. Thank you.
Thank you.
Yeah. Another question. So, I mean, what you talk about the co-design, right? Of doing this, right? I mean, is this something where the EDA vendors, the usual EDA vendors, or even emerging EDA vendors actually have design flows for incorporating the design for obviously for reducing susceptibility, as well as reducing emissions, all those kinds of things, right? Is this something that we have a standardized flow for that's emerging, or this is like a hotbed for startups, or this is perhaps one of your startups coming up? What's available?
Yeah, very nice question. So yes, that's actually the we need to set up a new framework because that normally the co-design means the sometimes just only for the power delivery network design or try to reduce the noise. But obviously, if we design the things from both the EMC and the hardware security point of view, that we need to include all those considerations together in the single design. This is the meaning of the co-design. And at the same time that we will have the mitigation options like circuit techniques, packaging techniques, and the new materials as well. Those needs to be combined in the same design environment. But this is the meaning of the co-design from my point of view. Yes, that we need a new startup company or new framework to complete this.
I see. And maybe what we need to do is to somehow convince the hackers to be involved in this business, right?
Yeah, that's interesting. As I mentioned, that the designers needs to be hacker, because that their approach are well learned by the designers.
I'm always very leery whenever, or skeptical whenever I need to hire a locksmith to basically break into my door or something like that, because I wonder if they've had criminal records before, which then probably means they're not so good as as locksmiths, perhaps, and that's why they're being locksmiths, because I shouldn't say that. But anyways, okay.
Interesting thing is that always the secure chips are going to the public, and the people are trying to make some attacks on that. So in the whole world, they will give you some answers. You don't need to hire the person with the criminal records. I think the whole world, someone will try and someone will report the big results, and that will be learned by the designers.
Yes,
that's the whole sequence in the public domain.
I was going to ask, I mean, all these simulations that your group has done, right? I mean, do you need like some sort of supercomputer to, do these types of simulations? I mean, is this something you have to be very, very careful in what you do to make sure that you actually have a result that or a simulation that can actually be achieved in a reasonable amount of time? I mean, are these like really, really lengthy, like, week-long, month-long simulations?
Oh, that's a one of the important point. I think basically we needed to understand the mechanism in the leakage or in the creation of the EM problems. Once we understand, we can make a good macro model, and that will accelerate the simulations. I don't want to make things in the same netlist and try to solve. I don't want to do that. I think we will try to make a good model that capture the actual things happening in the backside of the leakage or backside of the EM problems. And my answer is we don't use the supercomputer, that we will try to have the good models. For instance, the combination of the EM data with the receiver, the performance. Those are typical example of how we can use the system level model with the the noise data. Those combination, the bottom model and the high level model, will combine together to give you the good answer.
Okay. Yeah. Anyways, it's I guess a 90-minute mark already. There's still a few more questions coming. What I would like to request is perhaps people, the participants who have questions, they can email you directly for an answer. Okay. Yeah, and that way we can return people back to their time into their regular day. I know it's also very, very late on your side, so really, really appreciate you staying up so late to make this a convenient time for people in the rest of the world. So Nagata Sensei, once again, domo arigatou gozaimasu. I will return back to Abira. Thank you.
Thank you very much.
Thank you, everyone, for attending the webinar. I put Professor Nagata's email in the chat, so you can email him if you have any questions. I also put the link to obtain a certificate of participation in the chat. And the webinar will be posted on the SSCS Resource Center within a week. And if you have any other questions, just send us an email. Thank you.
Thank you very much.
Bye.
Bye.